make sure you can do these by hand, even if you're checking with your calculator. All right, so we have a couple of things that are going on with our derivatives. So all semester we've been learning about derivatives. So now what we're going to do is take these derivatives, second derivatives, and talk about how it tells you a little bit about what the graph looks like. Okay, so hence its name, curve sketching. We're going to, hopefully, in 3 days of class time, be confident that we can sketch and do these problems. All right, so the first thing we need to know is, what does the first derivative tell you? It tells you a lot of stuff about a graph. We've already done the velocity part, okay? So if we're looking at whether a function is increasing or decreasing, we can do that by looking at the derivatives. Okay, so if we don't have a calculator, we can't graph it, how do you know where a graph is increasing or decreasing? So this says if your first derivative is positive, greater than 0 means positive, on an interval, then your function is increasing on that interval. And we've already done that when we were doing the velocity positive and negative, same kind of thing. So that's not really new, it's just a different way to say it. So this was where the velocity was positive, when we look for the little plus signs. So now we're going to say that's where your function is increasing. And then where the first derivative was negative, okay, that's where your function is decreasing. That's where your function, the velocity, would be negative. So we already did those, again, just calling it something different. All right, we've already talked about critical number. So this is just a review of what we did last class. Critical number is where the derivative equals 0 or where the derivative doesn't exist. Right, we already did that. And then we talked about if we have a local max or min, then that's definitely a critical number because the derivatives are 0 there, right? So any max or min is a critical number on your graph. All right, and then we have this first derivative test. It says suppose c is a critical number on a continuous function. It says if f prime of x, so if the derivative changes from positive to negative at c, then you have a local max. And if the derivative changes from negative to positive, then you have a local min. Okay, and that kind of makes sense, because think about it. If you're going from a positive first derivative, which means your graph was increasing, positive derivatives mean increasing, and then you change to a negative derivative, well, then that has to be a max right there. And obviously the second bullet would be the opposite. If you have a negative derivative, that means you're decreasing. And then you change to a positive derivative, well, that would be a minimum. And then if your derivative doesn't change at all, so if you have no sign change, and this is important, you can't just assume one of these two things is going to happen. You have to test the numbers. You remember the little number line? We're going back to that. So if it doesn't change at all, then you have no max or min. So you can't assume that there's something going on there unless you check it. All right, so all that has to do with the first derivative. Then, now we're going to find the second derivative, and that tells you about concavity. Okay, so if you remember anything from your algebra days, concave up is kind of like a bowl shaped this way, right? So this is a concave up graph, and then this would be considered concave down. Turn it upside down. Okay, so concavity has to do with second derivative. So it says if the second derivative is positive, then your function is concave up. If your second derivative is negative, then your function is concave down. So I'm going to add some signs right here because this is what I use. Okay, so basically a graph takes on one of 4 shapes. Okay, so this graph right here, this piece of the graph would be increasing, and it would also be concave up. Okay, this graph is still increasing, pin's going up, but it's concave down. So you have to be able to tell which is which when we're doing these sketches. All right, so increasing slope. If we're doing increasing, I'm going to use an up arrow to represent increasing. I don't want to use a plus sign anymore because plus sign will mean increasing and plus sign also means concave up, and that gets confusing. So we need to kind of have different signs for that. Okay, so I'm going to use an up arrow for first derivatives where they're increasing. So this is where your first derivative is positive, right? Greater than 0. First derivative tells you that you're increasing if it's positive. Okay. Decreasing slope, so I'm going to use a down arrow, means it's decreasing. And that's where your first derivative is less than 0 or negative. And we did this with velocity. Okay, it's exactly what we did when we did those little graphs with velocity. So these would have little plus signs, these would have little minus signs. All right, and then concave up, I'm going to use that symbol for concave up. And this is where the second derivative, f double prime, is positive. And obviously for concave down, I'll use an upside down U. That's my notation for concave down. And that's where your second derivative is less than 0. Negatives. So for some of you, this gets confusing. So you need to understand that this is concave up, so is this. Okay? So if you put these two together, this piece, and then you tack that on right there, that's all concave up. Okay? And then this is concave down. It's part of the upside down, and so is this. So for some of you, that gets a little confusing until you practice and draw it. So you have to be able to see the difference in how it looks. But those are the only 4 shapes your graph's going to take on. Okay? So one of those 4 pictures is what we're going to be doing. All right, any questions on that? All right, so let's talk about concavity then. Continuing with second derivatives, then where your graph changes from concave up to concave down, those are called points of inflection, or inflection points. Okay, so hopefully you remember that. Somewhere in algebra you learn that. All right, so I gave you a couple of different graphs. Okay, so all of the little open circles, they should really be closed, but they're just to point them out. Those are your inflection points, okay? So if I look at this graph, here's concave down. All of that is concave down. And then right here, at that point, it changes to concave up. So where a graph changes from concave up to concave down, those are called points of inflection. And they look a lot different, depends on the graph. Okay? Now, that's where the second derivative equals 0. So points of inflection are where the second derivative equals 0. What do you have where the first derivative equals 0? What are you looking for when the first derivative equals 0? Critical numbers, which are your possible max and mins, right? So where the first derivative equals 0, those could be max or mins. Where the second derivative equals 0, it could be an inflection point. How do you know when I say the word could? Well, it could be until you test what's going on around it. Do the little number line. You have to show that on one side you have a plus, on one side you have a minus. Because then that means it changes, and then that is what it is. So it is a max or min if it's first derivative. It's point of inflection for second derivatives. Okay? All right, but I want you to look at this because what's the first derivative at this point of inflection? Positive, negative, or 0? Based on this graph, what sign would you get for the first derivative right here? Negative. You would get a negative sign because this part of the graph is decreasing. So the first derivative right here at this point is a negative number. The second derivative right here at this point is 0. Does that make sense? Okay, look at this point. What would be your first derivative? Positive, negative, or 0 right there? Here it would be 0 because this has got a horizontal tangent line. So this point has a first derivative of 0 and a second derivative of 0. And I want you to understand that because if it's a first derivative of 0, is it a max or min? This is not a max or min. So remember, it's a possible max or min. I got a first derivative that's 0, but I have to test around it. And if I test around it, I would get minus minus because this is still decreasing. So it's not a max or min, but the second derivative, this is a point of inflection because this is concave up and that's concave down. So you got to be careful with your testing. You can't assume anything on these because that's what's going to happen. All right, what kind of first derivative does this point have? First derivative, this is increasing, so this would be a positive first derivative, but the second derivative would still be 0 because that's a point of inflection. So there's 3 different cases where your first derivative is negative, first derivative is 0, first derivative is positive, but all of your second derivatives on those would be 0. Sorry. Okay, so you got to look at these graphs. This is so important that you can see what derivatives are doing when you look at a graph. Because on Monday, today is about looking at the graph and telling me stuff about the derivatives. Next week, I'm going to give you derivatives. You got to tell me what the graph looks like. So you have to get this today and by Monday so that we can move on. Because if you're stuck, then it's going to get even worse. as you know, you need to build on this stuff. So make sure this is making sense to you. So I'm spending time on it. I know we're not going to finish this today, but I want to make sure that you're okay with this stuff because this is huge important for your final exam and your last test, obviously. All right, so second derivative test. So if the first derivative is 0, think about that. What does the first derivative equal 0 mean? Possible max or mins. And the second derivative is positive, which means what? Concave up. Then what has to be true? If that equals 0 and the second derivative is concave up, what's the only place on concave up graph that has the first derivative of 0? Has to be a minimum. So that's what that says. So now we're testing, okay, this is a possible max or min, but as soon as you get that the second derivative is positive, it has to be a minimum. There's no other place on a concave up graph where your first derivative isn't 0. All right, and then opposite, you've got a first derivative equal to 0, possible max or min, but as soon as you find that the second derivative is less than 0, that means concave down. And so the only place on there to have a first derivative of 0 would be at a max. Okay? All right, so please make sure, go over that stuff, make sure that all makes sense to you. So we're going to work on probably today just the equation part of these notes. And these are some doozies. So Dr. Taylor did the easy one. We're going to do a couple of the harder ones. And this is what your WebWorks is about. So I would say do these on paper, make sure you're good, and then use your calculator to check. I mean, why not? You guys have one. You have a calculator handy. Okay, so the first thing I would tell you about all of these problems is you have to know the domain. You have to know the domain because if I don't, then your intervals are going to be wrong when you list, okay? So I want to know what's the domain of number 4. They give you that. They give it to you. What is the domain of number 4? It's right in the problem. It's right there, right? So when you give answers, you cannot give me negative infinity on the left and positive infinity on the right. Okay, you have to stay between 0 and 2 pi, and you can't even use 0 and 2 pi. I think you have one just like this on WebWorks, but it says greater or less than or equal to. So that would change that you would use brackets instead of parentheses maybe. All right, so there's your domain. So for every problem, you have to know that because that changes how you write your answers. Okay, so we're going to find all the critical numbers, the intervals where these things are increasing and decreasing. We're going to state if each critical point is a max or min. So all of part A and B have to deal with the first derivative. So since we're doing function g, that's all about g prime. C, inflection points and where this thing is concave up and concave down. So C is about the second derivative. Okay, and then we're going to sketch the graph without looking at the calculator. We could use the calculator, but we should be able to sketch it based on what we get from that. All right. So we're going to start with, I'm going to do the work over here, and then I'll do the answers over here. Okay, just so kind of keep things situated. All right, so let's start with the derivative. First derivative. So your function is x plus 2 cosine of x. So the derivative of x is 1. And the derivative of 2 cosine x would be minus 2 sine of x, right? The derivative, leave 2 out front, and then the derivative of cosine is negative sine. So that just changes that to 1 minus 2 sine of x. Okay, so how do we find critical numbers? We set the derivative equal to 0. Okay. So we're going to set this equal to 0. And we're going to solve that. Good old trick. All right, so we're going to move the 2 sine x over, make it positive. So 1 equals 2 sine of x, divide by 2. And then take the inverse of both sides since we're looking for x. So the inverse of sine is arc sine. So sine negative 1. All right, so where between 0 and 2 pi is the sine equal to 1/2? So what angles have a sine of 1/2 that's above the x-axis? So that would be at pi over 6 and 5 pi over 6, right? At 30 degrees and at 150 degrees. All right. All right, so part A says find the critical points. So we can start with that. So over here I'm going to put part A. So our critical points, and that's a point. So I got to do pi over 6 something and 5 pi over 6. So I got to give the point. So where do I plug in those values to always get y? Original function, right? All right, so I'm going to put these in y equals because we're going to be using them quite a bit. Make sure your calculator's in radians. So I'm going to put in x plus 2 cosine of x. All right. Then I'm going to go to my table, and I'm going to put in pi over 6, so second, pi divided by 6. So again, I'm putting it in just like that. It's going to change it to a decimal when I hit enter. That pi over 6, and 5 pi over 6. All right, so there's my points. I'm just going to round it a little bit. So we'll call it 2.26 and 0.89. Okay, so I'll just round them 2 places. So there's my critical points. Now it's also asking me to find where this thing's increasing and decreasing. So that's the little number line. Okay, so I'm going to G prime. Oops, move that over. All right, and I'm going to do a number line, but I can only go between 0 and 2 pi. So I'm just going to put parentheses here for 0 and a parentheses over here for 2 pi, because you can't go past that. So that's where the difference is. You can't put little arrows there, go from negative infinity to infinity. And I'm going to mark pi over 6 and 5 pi over 6, which are both less than pi, because pi is in the middle. So pi over 6 is way over here. And then I'll put 5 pi over 6 a little bit before halfway. And it doesn't really matter, as long as you kind of, I'm just trying to remind you. 6 pi over 6 is pi. So it's close to pi, but not quite. All right, and then remember we got to do test points. All right, so I got to pick some numbers in between here. So I'm going to show you kind of how I would do this now that we have a calculator. So I need a test point between 0 and pi over 6. I usually just take half of that. So something between 0 and pi over 6, I'll call it pi over 12. And you could do pi over 8, pi over 10, anything smaller than that. All right, something between pi over 6 and 5 pi over 6, it's easy. That's 90 degrees, so that would be pi over 2. And then something bigger than 5 pi over 6, pi would be good. Okay? So those are my test points. So remember we got to do our little plus and minuses, except I'm not going to do plus and minuses here. I'm going to do up arrow, down arrow. Okay? Because this is the first derivative. That tests where your graph is increasing and decreasing. Notice I put G prime here. So when I test these numbers, where am I testing them? Back in the original function? In the derivative. No, when I'm the only time you use the original function is to do what? Y's. Okay, when I'm getting y, then I need the original function. But when I am testing about the first derivative, so I have to put this in here, okay? So don't clear out y1 because we're going to need to get some more points. So here's what I would do. You just got to keep up with it. So go back to y equals, and in y2, you're going to put the derivative. So the derivative is 1 minus 2 sine of x. Now you just need to remember in your table, y1 is your y values, and y2 is the derivative values, right? Okay, so I'm going to go back to my table. All right, I'm going to clear these out just so they don't confuse you. And now I'm going to do my test points. So now I'm looking at, what do I care about? All I care about is if they're positive or negative. And this is the first derivative over here. So I'm going to put in pi over 12. Oops, that's not pi. Pi divided by 12. I'm going to put in pi over 2. And I'm going to put in pi. All right, so this is what I care about. I don't want the y values. These are the y values. I want the derivative values. So positive when I was at pi over 12, so that's an up arrow right there. So up arrow between 0 and pi over 6. My next test point at pi over 2, I got a negative 1, so that means this graph is decreasing between pi over 6 and 5 pi over 6. And then over here, at pi, I got 1 again. So the rest of the graph is increasing. All right, so now I can answer the rest of part A. Where is this graph increasing and decreasing? All right, so it's increasing where my up arrows are. So between 0 and pi over 6, union with 5 pi over 6 to 2 pi. I can't go to infinity. So wherever you have up arrows, those are increasing parts of your graph. And then it's only decreasing in the middle between pi over 6 and 5 pi over 6. Okay? All right, so that's part A. All of part A has to deal with the first derivative. Now I can answer part B. I don't have to do anything else for part B. Now state whether each critical point is a max or a min, or neither. Okay, remember, it could be neither. Okay. All right, so our first critical point was pi over 6. What was going on to the left of pi over 6? We were increasing. So your graph's going up. And then to the right of pi over 6, we were decreasing. So we were going up and then down. So what is pi over 6? Has to be a max. So we're going to say there's a max at x equals pi over 6. We'll get the y value in just a minute. And then our other critical point was 5 pi over 6. So what was happening around 5 pi over 6? We were going down, decreasing, and then increasing. So 5 pi over 6 has to be a minimum. So we have a minimum at x equals 5 pi over 6. Now, what if they asked you for the points? The actual ordered pair. Where do I get the ordered pair from? I'm going to plug these numbers into the original function, right? So that's why it was nice to kind of already have this. Oh, I didn't put those in, did I? Yeah, I did. We already did that. Okay, so we already have those. My bad. All right, so we already had the ordered pairs up there. So we have those if you have them. All right, so that's the answers to A and B. Now, part C, same exact thing, except we got to do a second derivative. Okay, we're going to do the same thing for part B. All right, so we need g double prime of x. So remember, here's your first derivative. So we want the derivative of that. So what's the derivative of 1 minus 2 sine of x? Derivative of 1 would be 0, and what's the derivative of negative 2 sine of x? Negative 2 cosine of x, right? Keep it negative, because the derivative of sine is cosine. All right, so now we're going to set that equal to 0, solve that. Got to do the same thing with this. Okay? So we're going to set negative 2 cosine of x equal to 0. We're going to divide by negative 2. Move that up a little bit. So 0 divided by negative 2 is still 0. And then take the inverse of both sides. All right. So where between 0 and 2 pi, so all the way around the circle, where is the cosine value equal to 0? So that would be up at the top, right, at 90 degrees, and then at the bottom at 270. So that is pi over 2 and 3 pi over 2. Okay. Top and bottom is where the cosine equals All right, so we're going to do the same thing. We need another number line, so I'm running out of room, so I'll do that over here. Now, this time we're testing the second derivative. So I'm going to put g double prime. Okay. Because where do I test these points? These points are now getting tested in this function. So when you do your number line, I'm saying this slow and precisely because it's important. So when you're testing a second derivative, then you're going to plug your numbers into the second derivative. That's how you know if the second derivative is positive or negative. Okay? When you're doing first derivative stuff, you got to put those numbers in the first derivative. So I always label these number lines because you're going to have several of them. And this way you're just kind of helping yourself not make that mistake. All right, so I'm going to put these 2 points on here, pi over 2, which is about 1/4 of the way, that's 90 degrees, and 3 pi over 2. So I need to pick, again, 3 test points in those 3 areas to see what's going on with concavity. So now I'm talking about where this graph is concave up, concave down. All right, so pick something between 0 and pi over 2, so I'm going to pick pi over 4. Pick something between pi over 2 and 3 pi over 2, I'll pick pi. And something between 3 pi over 2 and 2 pi, I'll keep with 45 degrees, so that's 7 pi over 4. This is why it's helpful to know that unit circle. Now you could say 315 degrees. You can use your degrees, that's fine, because the sines and cosines don't change. I'm just keeping us in radians because that's what you need to know. All right, now, I'm going to go ahead and just plug this into here. You could put this into y3, and then you'd have to move over on your table, but let's just do this in our head just to save time. All right, so I'm going to put pi over 4 into the second derivative, negative 2 times the cosine of x. So we can do this. So the cosine of x, cosine of pi over 4, we agree is a positive number. Doesn't really matter what it is. It's positive, times negative 2. So that's a negative number right there. So everything between 0 and pi over 2 is concave. Oh, it's not a minus sign. Sorry, concave down. We're doing concavity here. So this is why I use these symbols. Otherwise, I got a bunch of plus and minus signs, and it gets kind of confusing. It's already confusing. So, all right, pi. Find the cosine of pi. What's cosine of pi? Negative 1. So negative 1 times negative 2 is a positive number. So that's concave up in the middle. And then 7 pi over 4 cosines positive, square root 2 over 2 again, times a negative number. So that's concave down. Okay, so minus, plus, minus, but I'm using my concavity sign. All right, so C says find inflection points and find the intervals for concavity. All right, so where do we have inflection points? Remember, inflection points only happen where you have a change from concave up to concave down. So, is pi over 2 an inflection point? Yes, because I went from concave down to concave up. So, inflection point is at pi over 2. I got to find the y value in a minute. Is 3 pi over 2 an inflection point? Yes, it went from concave up to concave down. So, I got 2 inflection points. All right, now where do I find those y values? Original function. So now I'm going back to my calculator. Clear these guys out. Okay, now remember, I'm putting it in the original function. So now I want to look at the first column. Okay, so go to your table, and I'm going to put in pi over 2. So that ordered pair is 1.57. And then I'm going to put in 3 pi over 2, 4.71. Okay, so those are the ordered pairs. It's the only time you use the original function. All right, and then where's this thing? Where are the intervals? So this thing is concave up. You got to give the interval where it's concave up, which is just in the middle. So between pi over 2 and 3 pi over 2. And then it's concave down 2 places. So between 0 and pi over 2, and union that with 3 pi over 2 to 2 pi. Now, if your domain was all real numbers, then obviously that would be a negative infinity and that would be a positive infinity. But this one gave you a boundary, so, okay. All right, last thing is to try to sketch this without graphing it. So I'm going to cover this up and do this on another sheet of paper because I don't have enough room. All right. Now, I know I'm going between 0 and 2 pi. So when I do my sketch, and I think all this is above the x-axis. So let's just remember, here's pi, and here's 2 pi, just so we kind of get it correct. Okay, now I'm plotting points. So now I want my ordered pairs, which I have most of them up here. But let's go from 0 to 2 pi. So I'm going to go back to the original function. If you put 0 in here, what do you get? 0 plus 2 times the cosine of 0. Cosine of 0 is 1.
2.
So 0 plus 2 is 2. So here's 2. So at 0, you're at 2. And then at 2 pi. 2 pi is 6.2 something, right? 2 times 3.14. So if I put in 2 pi here, that's a little bit more than 6. And then the cosine of 2 pi is 1 again. So 6.2 plus 2 would be 8.2. So let's just go up here and call that a little bit more than 8, whatever it is, 8 point whatever. Just so we know. All right, so that's the start of my graph. There's the end of my graph, just so we have that. All right, now let's plot our 2 critical points. So pi over 6 and 5 pi over 6. So remember, 5 pi over 6 is 30 degrees, so real close to 0. And then 5 pi, that's pi over 6, sorry. Pi over 6 is over here. And then 5 pi over 6 is real close to pi. All right, so we're going to plot those points. So pi over 6 is at 2.2, so a little bit higher than where we started. And then 5 pi over 6 was 0.89, so less than 1 down here, right? And what did we say happened at pi over 6? It was a max, right? And at 5 pi over 6 was a min. Okay, so that seems right. We're going to go up, and then it's going to come down, and then we should go back up, right? Looking at this. All right, so let's look at our points of inflection then. All right, where were our points of inflection? Pi over 2. So where would pi over 2 be? Halfway between 0 and pi, right? So here's pi over 2. And its ordered pair was 1.57. All right, so look at that. We went up. Oop. We went down. Okay. Now, is that concave down between 0 and pi over 2? That's concave down. That's what we got. 0 to pi over 2 is concave down. All right, then our next point of inflection was at 3 pi over 2, which is way over here in the middle of pi and 2 pi. And that ordered pair was 4.7. So I'm just estimating, guesstimating where 4 is. All right, where were we concave up? Remember, between pi over 2 and 3 pi over 2. So if I continue this, that is all concave up. And what happened at 5 pi over 6? We had a minimum, which is what we said. We had our max at pi over 6. There's our minimum. This is concave down, so there's a point of inflection. This is all concave up, point of inflection. And then what happens between 3 pi over 2 and 2 pi? We have to be concave down again, which is that. And then it's exactly what we got. Okay, so if you graph that, that's what you would see. Kind of cool. We can do it all without. Takes a long time, but we can do it. Okay, so it's kind of interesting how all of that works. So we're going to stop here for today. I know we didn't get too far on this, but I need to do this slow and precise with you because I can't tell you how important this stuff is, even for Calc 2 use and Calc 3. So we got to have that down. All right, so we stop recording now. All right, so we're going to pick up from where we left off last week. So that is number 5 on section 4.3. So we can start recording now. All right. So today and Wednesday, we're going to be working on this, finishing up section 4.3, which is again about the functions. And then we'll get into hopefully a little bit of curve sketching today and then finish that up on Wednesday, okay? All right, now, this problem really is given to you. I put this on here because it's one of your web work problems, and it's just nice to kind of have a guide for you to go through it, okay? So let's look at that. Remember, for all of these problems, the first thing you need to know is what is the domain, because the domain is going to kind of guide you on how you're going to write your intervals, okay? All right, so can we make it a little bit bigger? Trying to get that function. Okay, that's good, thanks. I know it's kind of small for you guys in the back. All right, so looking at this function, e to the x over e to the x plus 8. Tell me what the domain is for this function. Any ideas? Are there any problems? Can I put anything in for x? Can I work it out? Is there any?
Whatever makes e to the x equal negative 8.
Negative 8? Is there anything that would do that? What is e to the x? Isn't that always positive?
Yeah.
Right? So remember what e to the x graph looks like. It's above the x-axis, right? So this is always positive. So there's no way for me to get 0. So my domain for this problem is all real numbers. So I'm just going to write that over here. Remember, that's important, because that changes our intervals. That changes, how we write the intervals. Remember, for the last problem, I'm going to slide this up for a minute. The last problem, remember, the domain was only between 0 and 2 pi, so that's how we had to give our answers. So here, when we give our answers, we get to go from negative infinity to infinity. Okay, so same rules. Find the critical points, the intervals where this thing's increasing and decreasing. State whether each critical point is a max or min. So that all comes from the first derivative. So we have to do a quotient rule to find the first derivative and to find critical points. Okay, so we're going to do h prime. All right, so quotient rule. All right, so the derivative of the top, which is e to the x, that derivative is e to the x, times the bottom, leave it alone. Okay, minus the top function, e to the x, times the derivative of the bottom. Okay, what's the derivative of the bottom function would be e to the x, and then 0 for the 8, right? So we just have e to the x times e to the x. All right, all over the bottom squared. Okay, so let's simplify that a little bit and see what we get. All right, so on this one, I'm going to go ahead and distribute. So e to the x times e to the x is e to the 2x. And then e to the x times 8 is 8e to the x. And then if I multiply e to the x times e to the x again, I get e to the 2x, and that's minus e to the 2x. So those are going to cancel out on the top. Okay. Okay, with me?
When those multiply the, oh, never mind, here, sorry.
Yeah, you add the exponents, right? So 1x plus 1x. Yeah, not x squared. Be careful with that. Well, luckily, if you did it the wrong way, they'd still cancel out. On this one, it'd be okay. All right, so these are going away. So we left with 8e to the x over e to the x plus. Okay. Now, to find critical numbers, we're supposed to set the numerator equal to 0 and the denominator equal to 0 and solve. However, we just said e to the x is always positive, right? There is no way you're going to make 8e to the x ever equal 0. It can't happen. And e to the x plus 8 squared is always positive. So this numerator is always greater than 0, and this is always greater than 0. Okay, just by the fact. Now, you could try it. If you set 8e to the x equal to 0, you divide it by 8, When does e to the x equal 0? It doesn't. Okay, so you can't solve this. So that means there's no critical numbers for the first derivative, which means there are no max and mins. So all I need to know is this graph increasing or decreasing? Well, if the derivative is always positive, that means it's always increasing. So we can answer A and B pretty quick with all of these, because there's not a whole lot going on. So for part A, okay, there's no critical numbers or critical points. And this thing is always increasing. So it's increasing from negative infinity to infinity. Okay, because the derivative is always positive. The numerator is always a positive number. Denominator is always a positive number. So all numbers. So it's not decreasing at all. It's always increasing. And part B, there are no max and mins. And getting critical numbers to check. All right. Okay, so that's all the first derivative stuff. Wasn't very exciting. All right, now we have to find the second derivative to do part C. So what am I taking the derivative of? This is the part when you clean things up. I don't want to take the derivative of this. That's not nice. So I'm going to take this derivative. So here's the first derivative when we cleaned it up. Right? That's what we're getting ready to take the derivative of. Let's use that. So just another quotient rule. Okay? All right, so we good on parts A and B? Any questions? So that one is a little different. That's why I put it on here, because e to the x is since it's always positive, that kind of throws off answers a little bit. All right, so we're ready to do our derivative of the derivative. So derivative of the top would be 8e to the x times the bottom, leave it alone. And minus the top, 8e to the x. All right, now, times the derivative of the bottom. So this is a chain rule. Okay. So the outer function is something squared, so we're going to do that first. So the derivative of something squared is 2 of those somethings, right? So we're going to bring the 2 out front, leave the inside alone, and then it would be to the first power, but we don't need to put a 1 there. And then times the derivative of the inside. And the derivative of the inside, we already did that, was e to the x. All right, and then all over the bottom squared. So that's going to put the denominator as e to the x plus 8 to the 4th power, right? Square, square. Okay. I'm going to go ahead and factor this. I don't want to simplify this. So I think you can see the factors better. So look at the top. So we got 2 terms. We've got this whole piece and then minus this whole piece, right? All right, so I'm going to factor stuff out to make it a little bit easier. So do we see that both terms have an 8e to the x? Okay, so I'm going to factor that out front. And both terms have 1e to the x plus 8, right? So I'm going to factor that out. All right, so that's my factor. So now I'm going to factor my 2 terms. Okay, so I'm going to take an 8e to the x and 1e to the x plus 8 out of both sides of this. All right, so what's left over here on the left side? If I
E to the x plus 8.
Right, so I have 1 more e to the x plus 8 over here, right? So that's the first part, e to the x plus 8. Okay, minus.
2e to the x.
Look over here and tell me what's left. If you take out the 8e to the x and the e to the x plus 8, you're left with that 2 and that e to the x. All right. Okay, this makes it a little bit easier because now I can get rid of that e to the x plus 8. Okay. All right, so I am going to get rid of this e to the x, the one that's being multiplied, with one of the ones in the denominator. Okay, not this one. I can't touch that one because this is being subtracted. But so this one is going to go away, and that's going to make 3 in the bottom, not 4 of them in the bottom. Okay, so now we have 8e to the x times e to the x plus 8 minus 2e to the x all over e to the x plus 8 cubed. All right, and we can simplify that bracket. So we have 8 e to the x times what? So we have 8, I'm going to put that out front because it's positive, and then e to the x minus 2 e to the x would just be minus e to the x. Get rid of one of those. All right, and now I'm only simplifying because I have to set this equal to 0. Good news. If we have to set each factor in the numerator equal to 0 and each factor in the denominator equal to 0 to find our critical numbers for the second derivative, we already said that there's no way this is going to be 0, right? So that right there, this one is always positive, that piece. So it's always greater than 0, that's what that says. Chicken scratch up here. So this one is always greater than 0. What about the denominator?
Also always greater.
This is always positive. E to the x is positive. If you add 8 to it, positive, cube it, positive. So this guy is always greater than 0. The only thing that's going to give me a critical number is right here. So this is the only piece I have to set equal to 0 and solve. Okay, so take 8 minus e to the x, set it equal to 0, because that one will give me an answer, since it's subtracting. So I'm going to move the e to the x over to the right to make it positive. And then I got to write this as a log. So I'm solving for x. So the natural log of 8 equals x. And the natural log of 8, that's a number, 2 point something, a little bigger than 2. All right, I'm just going to leave it like that. All right, so I need to find in part C inflection points and where this thing is concave up and concave down. All right, so first off, I'm going to do part C. Let's do our inflection point. So that's going to be the natural log of 8. You can use the decimal. I don't know what it is.
2.87.
I just leave it like that. But if you want to write the decimal, if it makes you happy. 2.07. Okay, because some of you don't think that's a number. So there's 2.07. So where do we plug the natural log of 8 to get the y value?
In the original. Well,
In the original function. All right, so I don't need my calculator for that. Because e to the natural log of 8, the e and that natural log cancel out. So that's 8. Okay, so e to the natural log of 8 is 8 over e to the natural log of 8 is 8 plus 8. So I get 8 over 16, that's a half. Okay, now you can put it in your calculator, that's fine. But, all right, so we get the natural log of 8, 1/2. There's our inflection point. Now I'm going to do my little number line over here. Here's the natural log of 8, which remember is a little bit more than 2. This is h double prime. So where do I get my pluses and minuses? I get that from the second derivative, which is right here. This is the simplified version. Okay, so we're going to pick something smaller than the natural log of 8. 0 is good. Pick something bigger than the natural log of 8, let's say 3. And we're going to plug it in here. Now again, this first part of the numerator and the bottom is always positive, so I don't need to put it in there. All I got to do is check this. This is always positive, this is always positive. So all I need to know is what's happening here. So if I plug in 0, okay, e to the 0 is 1. 8 minus 1 is 7. That's a positive number. So this side is concave up. Remember, this is second derivative. So I'm going to use the, not a plus sign, but the u, concave up. And if I plug in 3, e to the third is bigger than 8, right? E to the third is 8 point something. So 8 minus e to the third is going to give you a negative number. So that means this side is concave down. Okay. Now actually, I should have done this first. I kind of knew it, so I jumped the gun on this one. Remember, you can't say that that's an inflection point until you know that there's a change. So you should have done this first. I just jumped the gun on that one. So I know now that the natural log of 8 is an inflection point because it changed from concave up to concave down. And then I found the y value of the inflection point by plugging this into the original function. You always get y from the original function. Okay? All right, so concave up would be from negative infinity to the natural log of 8, or 2.07. And then it's concave down over here. So that's still part of C. So concave up would be from negative infinity to the natural log of 8. Concave down from the natural log of 8 to positive infinity. All right. Quick graph. This one not very exciting, but quick graph of this. So our only fun point is the natural log of 8, which is a little bit more than 2. So here's 1, 2, 3, and 1/2. So let's make that 1/2 and 1. So right about there is our inflection point, a little bit bigger than 2, 1/2. This graph was always increasing, right? So we have to do that when we draw it. It's positive, it's going to stay above the x-axis. So what's happening to the left of the natural log of 8? It's concave up, but increasing. So that's increasing, concave up. And then after the natural log of 8, we're going to be concave down, but still increasing. So if you try to put that in your calculator, it'll look similar to that. Okay, so that's all that graph does. It's always increasing. Okay. It's always positive. Concave up on one side, concave down on the other. Okay? All right, that was a fun one. Now, for the most part, if you guys have a calculator, you're going to be graphing this and kind of looking at it. So if you're doing WebWorks and you just plug this into your calculator, you can see that it's always increasing. You can see where it's concave up, concave down. Okay, so remember, a lot of these sometimes are on the non-calculator part of your exam where they ask you these kind of questions, or it could be the free response, and sometimes they give you variables. Constants like e to the a or something. So you have to understand, what these things look like. So fine using your calculator to check, but do it by hand to practice, okay? All right. Questions? All right. I'm going to pass the sign-in sheet around before I forget that. Also, don't forget Old Common Finals. They're posted on Canvas, so you need to start thinking about those. Okay? Start working on a little bit at a time. I think I put, like I said, 4 or 5 of them on there for you guys. I think maybe 4. All right. Now, on number 6, I'm going to do parts A and B by hand. Then we're going to do part C with the calculator, because this one you would not get this part C to do by hand, and it takes a really long time to find the second derivative, so we're just going to graph it, okay? Especially because after all the work, it doesn't really do anything exciting. So let's get through parts A and B by hand. That part's not bad. All right, so this is a radical product rule. So again, just practicing all our old rules. And this time we're going to clean them up because we have to set them equal to 0. All right, so where is this function, which is x times the square root of x plus 7, where is it increasing and decreasing? So that's first derivative stuff. So we have to find the first derivative, do our little number line, see what's going on. All right, so first derivative, product rule. Okay, so x is your first function, and then the square root of x plus 7 is your second function. All right, so we'll start with the derivative of the first. So the derivative of x is 1. Leave the second one alone. Okay, so 1 times the square root of x plus 7 plus the first function x. All right, times the derivative of the second. So remember, this is x plus 7 to the 1/2. So that is 1/2 x plus 7 to the negative 1/2. And then times the derivative of the inside, which is just 1, so you don't need that. So we have to set that equal to 0 and solve it. So I'm going to clean it up before I set it equal to 0. So over here on the left, 1 times the square root of x plus 7 is just the square root of x plus 7. Plus, and then the only thing in the numerator over here is x. The 2's in the denominator. And so is that square root of x plus 7. That's what I got set equal to 0. Now, the good news is, since we have 2 square roots of x plus 7, we're not going to have to worry about any kind of conjugates or anything, so that's good. All right, so what I'm going to do is move this term over here. Okay, so I'm going to do the square root of x plus 7 equals negative x over 2 square root of x plus 7. Can give myself enough room here to work. All right, so I'm going to put the square root of x plus 7 just so you can see it over 1, because now I have a proportion, and I can cross multiply. That's what I'm going to do to get rid of these fractions. And also get rid of the square root of x plus 7. All right, so look over here. We're going to take the square root of x plus 7 times 2 square root of x plus 7, if you cross multiply. So 2 times the 1 out front, and then what happens to the square roots of x plus 7? That gives you just the x plus 7, right? Square root times the square root. So that got rid of that. And then on the other side, we're going to do negative x times 1. So that's negative x. So now that's pretty easy to solve. So distribute and solve for x. All right, so we get 2x plus 14 equals negative x. Subtract the 2x over to the other side, that's negative 3x. So we get negative 14/3. Now, before I write or do my test points, I forgot about my domain. This domain is not all real numbers. So go back up. Tell me what the domain is of that function.
X is not equal to negative 7.
X has to be greater than or equal to what?
Negative 7.
Negative 7, right? I can't take the square root of something negative. So remember how you find the domain of radicals? Set x plus 7 greater than or equal to 0. Solve that. So the domain has to be greater than or equal to negative 7. All right, so when I do my number line, this point over here is negative. I can't go past negative 7, okay? So not infinity, not negative infinity. All right, so negative 14/3 is negative 4 and something. So put it close to here. All right, so we need a test point here, test point there. And this is first derivative, so we're testing in the first derivative, not in the original function. And your number lines go with your derivatives. All right, so something between negative 7, negative 14/3, let's just choose negative 6. And 0, always easy, on the right. All right, so if I put negative 6 in the derivative, okay, in the derivative up here. So if I put negative 6 in here, this is always positive, right? So square root of 1. Plus, but if I put a negative 6 right up there in the top, I'm going to have a negative number divided by a positive number. Okay, so that's going to give me negatives over here. So that's decreasing. And then if I put 0, this whole thing's 0, so this is a positive number over here. So that's going to be increasing. And you're welcome to use your calculator. I'm just doing it quickly in my head. But you're plugging those numbers into the derivative, not to the function. All right, so that means we are decreasing. Got to finish this answer up here for part A. I'm going to actually write part A answer down here. Just running out of room. So we're decreasing from negative 7 to negative 14/3. And remember, your increasing and decreasing intervals never use brackets. Even though you're allowed to use negative 7 in this function, increasing, decreasing, never use square brackets, always parentheses. All right, and then we're increasing on the other side. So negative 14/3 to positive infinity. So negative 14/3 is a max or min. Which one is it? Based on our arrows. You're going from decreasing to increasing. That is a minimum, right? So that's how I know that. So I'm going, this graph was going down, decreasing, and then increasing. So we have a minimum for part B at x equals negative 14 thirds. Where would you find the actual minimum value, which is the y value?
Plugging in 14 thirds to the
Original function, right? So what is the min? Okay, if I asked you what is the min, then you would plug in negative 14 thirds here, and you would get y equals, I think I already wrote that down somewhere, negative 7.12. Okay? So, because remember how WebWorks asks you things. This is where the minimum is at, and this is the actual minimum value, the y value. So, okay. So don't get those wrong. Remember, max and mins are y values, how high up and down you're going. All right, now for the other part, just again, because it is nasty to do the second derivative, and the critical point that, because I did this earlier, the critical point isn't even in the domain, so it's a lot of work for nothing. So I had to take the derivative of this, okay, which doesn't seem bad, but then you got to set it to equal and solve it, and it is kind of nasty. So I just stuck this thing in my calculator because this thing is always concave up. Okay, so if I look at the graph, here's negative 7 over here. And if I put negative 7 into here, I get 0. So that's where the graph starts. And then I know the minimums at negative 14 thirds, negative 7 down here. Bless you. Okay, so there's that minimum point. And then the thing is always concave up, so it goes like this. Oh, actually, it goes through 0, 0, I think. Yes, it does. So if I put 0 in there, yeah, so I did that right. All right, it goes like that. So this thing is always concave up, but when you write the interval for where it's concave up, it would be from just negative 7 to infinity. Okay. So you can plug that in. Okay. And again, I would do this with you, but I want to do other stuff today, and this takes a long time. You guys could try it. You would find the derivative of the first derivative. I'm going to just sit this up here. But you can look. This is what I was doing earlier. So here's the derivative. So there's the first term. Then I had to do a quotient rule. Then I had to simplify it, and then solve it. And then I ended up with my critical number not even being part of the domain. So this thing was concave up everywhere, so it was just a lot of work for nothing exciting. So, and you would not have to do one this terrible. I promise you that. Okay? I mean, it's doable. Those of you that like to do these and figure it out, that's a good one to do. So if you can do that second derivative and solve it, that would be awesome. You could automatically pass. No, I'm not going to say that because some of you would try that. All right. So let's move on then. So typically your second derivatives would be more like the ones we already worked on, okay? All right, so number 7 is just straightforward. This is WebWorks. So just looking at it, there's no work involved. So suppose that, I think that's supposed to be f prime. What the heck? Oh, I guess that is the second derivative. I guess the little things are backwards. All right. So let's suppose that the second derivative is continuous. So it's just a continuous function. And here's some information about the first and second derivative. So what does it mean that the first derivative at 5 is 0? What does that tell you about what's happening at 5? It's a possible what?
critical point.
Well, it is a critical point, but it's a possible what? Max or min, right?
Yeah.
First derivatives are possible max and mins. If the derivative is 0, it is a critical point. Okay, but what we don't know is it a max or min? So this could be a max or min. How do I know? Well, let's look at the second derivative. What does it mean when the second derivative at 5 is 6? That's a positive number. So what kind of, that's concavity. So is this concave up or concave down? If it's a positive second derivative. Concave up, right? So this is telling you the second derivative is positive. I don't care that it's 6. I just care that it's positive. So concave up at 5. So what's happening right there? Max or min?
Min.
Okay, think about it. This has a derivative of 0. The only place on concave up where the derivative is 0 is right there, right? So if the whole graph is concave up at 5, and it has a first derivative of 0, then it has to be a local min, okay, just based on that information. So I think B goes the opposite way. So at 19, they're telling you you have a possible max or min, derivative 0, horizontal tangent line. And at 19, the second derivative is a negative number. Well, if second derivatives are negative, those are concave down. And what point on here would be the only point where you have a first derivative of 0? Right there. It's the only horizontal tangent line. So that has to be a max. Okay, so you guys have to be able to start understanding what's given to you with these first and second derivative numbers. Okay? All right, I love number 8. This is the start of our curve sketching, so let's look at that. Okay. Now here's the thing for today and for Wednesday. We're going to be looking at a lot of graphs, so you can't use your calculator. All right. But you have to be very careful on whether or not these are the graphs of the function or a graph of a derivative. So you need to start thinking about the fact that a derivative, so far, all we've been doing with derivatives is given the equation, right? Like if the function is x squared, the derivative was 2x, right? Well, remember, 2x is a function. Okay? It is a function. So the derivative, I just want to mention that to you. If a function is x squared, here's x squared. Okay, that's the function. Well, the derivative of x squared, get that on my screen, is 2x, right? Well, that's also a function. What does 2x look like? 2x is the graph that goes through 0, 0, has a slope of 2, up 2 over 1. So there's 2x. So I can graph functions and I can graph derivatives, and that's what we're getting ready to do. Without this stuff, can you do this? Can you give me one or the other based on one of the graphs? So that's kind of what we have to do now. So you got to start wrapping your head around the fact that derivatives are functions, which means they can be graphed. Okay, they actually make a graph. All right, so we're starting with that now. Not too bad yet, but we're getting there. All right, so here's a function. This is the function. We're going to answer true or false based on what we're seeing. So notice these questions are asking you about the derivative or second derivative. So if you have a function, first derivative's about increasing and decreasing. So where this thing is increasing and decreasing is going to give you answers about the first derivative. Where this thing is concave up and concave down is going to answer questions about the second derivative. Okay, so that's what you got to think about with these. All right, so let's look at the first one. Is the derivative at 3 equal to 0?
Yep. Yes.
True or false?
That would be true.
Okay, we'll go to 3 over here. Does that have a derivative of 0? Is it a horizontal tangent line? Yeah. Yes, it's a max or min. It's a min. So mins will have a derivative of 0. So that's true. All right, number 2. The second derivative is greater than 0. So that means concave up. So is the second derivative, so is this function concave up between 0 and 2? So 0 and 2, right here. So what kind of concavity is this right here? That's concave down, which means the second derivative has to be negative there. So that is false. Okay? The second derivative is less than 0 there. Okay. All right, number 3. Is the second derivative greater than 0? So again, that means is your function concave up when x is less than 0? So is this piece of your graph concave up?
Yeah.
Yes, that's concave up. So that is true. So that second derivative of all those points they would be a positive number. All right, number 4, first derivative is less than 0. That means your graph is decreasing. Okay? If the first derivative is less than 0, that means your function has to be decreasing. Is it when you're less than 3? So is this function decreasing to the left of my hand. Yes, right, it's going down, going down. So that is a decreasing graph all the way to 3, so that would be true. And lastly, is the derivative of 0 0? Right here, does that have a derivative of 0? Yes, right, it's got a horizontal tangent line right there. It's a point of inflection, but it does have a first derivative of 0, so that one is true as well. Okay, so that's looking at a graph. All right, now, I just want to do a little bit extra with this one since we're looking at it. What if I asked you to graph the derivative of this function? Okay, graph the derivative of this function. All right, so if I'm looking at this, do you see another inflection point first off? There is another inflection point. This is an inflection point right here, but there's another one right about here, right? Because this piece is concave down and then concave up, right? So there's another inflection point. When you're doing graphs, because we're going to do this a lot, but remember that your max and mins of your function, those are where your derivative is 0, right? So if I asked you, where on this graph is the first derivative equal to 0? We already did that, 1 and 5. So at 1, the derivative is 0, and at 3, the derivative is 0. So 0 is the x-axis. Okay. And then your inflection points are the max and mins of your function, okay, of your derivative. Sorry about that. So your inflection points of your function are the max and mins of the derivative. So let me ask you this. What kind of slope does this part of the graph have? Negative or positive number? Negative, which means this is going to be a minimum because the most negative number you could get. So I'm just going to put a point down here. Okay? And then this is a max at 0. So if I were going to connect these points, here's what, so there's the graph of the derivative of this function, just based on max and mins and inflection points. Okay, so now I want to look at that with you. So this would be f prime. And I didn't have a function, just based on what a derivative does. So max and min, the derivatives were 0. Okay? Inflection points, which were here and here, are the max and mins of the derivative. Okay? So what's happening over here? Decreasing? What kind of slopes are decreasing numbers? Negative, right? So the derivative, any point down here on the derivative means those were negative numbers, right? Y's are negative down here. So look at this. All of these numbers on the derivative are negative till I get right here. And didn't we say that this graph was decreasing all the way till we got to there? So that means every one of these first derivative numbers has to be negative, which means they have to be below the x-axis. And that's exactly what this is. And then right here, we started increasing, which means now our derivatives are positive numbers. Okay? So we will work on this. I don't expect you to kind of get that now, but that's kind of what we're going to be doing, is taking graphs and figuring out sketches for their derivatives and going the other way. Okay? So you didn't have to do that on that one, but I like to do that just because you need to sort of start seeing that now so that we can work on that probably Wednesday. Okay? All right, so let's finish number 9. I've seen this problem on the final exam maybe a couple times in the past few years. It's one of your web work problems. I typically don't give it to you on my test because it takes too long to work out, so we don't have a lot of time. But it is a good problem. It's just that you understand derivatives and so forth. All right, so number 9 says, find a cubic function. So basically you need to find the values of a, c, and d. That's what it's asking you for. So find a cubic function that has a local max of 8 at x equals -2. Okay, and it has a local min value of 6 at x equals 0. So let's talk about these points. Okay, let's start right here. I'll put this information right underneath here. If we have a local max of 8 at x equals -2, give me a point on f of x. What is a point on f of x? You already know that. What's the ordered pair? We have a local max of 8 at x equals negative 2. So what's the ordered pair? Negative 2, 8, right? So that's what that means, right? So giving it to you in a weird way. So at x equals negative 2, the value is 8. That's the point. But since it is a maximum, then what is f prime of negative 2 equal to? What's the derivatives of max and min? 0, correct? All right, so that means a point on f prime would be negative 2, 0, right? That's a point on the derivative. Think about that. Okay. Right. So if I'm looking at a graph and I see a maximum, it's telling me the maximum's at negative 2, 8. So it goes like that, at negative 2, 8. So right there at negative 2 has a horizontal tangent line, which means its first derivative is 0. And first derivatives are ordered pairs on a derivative function. So that would be an ordered pair. All right, let's do the same thing over here. Minimum value of 6 at x equals 0. So first off, tell me the point on f of x. So we have a minimum at 0, and the minimum value is 6. So that ordered pair would be 0, 6. So that's a point on my function. Okay? But the derivative at 0, the derivative at that minimum value is 0. So we got a concave up part of the graph. So that derivative down there is horizontal. So then we have a point on f prime, 0, 0. So we got lots of ordered pairs now. So now we can find our value. Okay. So just pay attention to the points on the function and the points on the derivative. So let's start with the function, f of x. ax cubed plus cx squared plus d. F of x, so let's plug this point in and see what happens. Okay, plug in 0, 6. So y is 6, x is 0. So we get 6 equals d, right? 0 plus 0 plus d. All right, so I found d, right? So now I know that f of x is ax cubed plus cx squared plus 6. All right, and now I got one more point on f of x, negative 2, 8. So now I'm going to plug negative 2, 8 in here. Okay, so 8 is y, x is negative 2. Okay, and we're going to solve that. So I took both my ordered pairs that were on f of x, see what I could do with it. So I did find d. That was good. Now I'm going to get stuck, but let's just see what happens. So negative 2 cubed is negative 8a plus 4c, that's positive, plus 6, and then I can move the 6 over. So I get 2 equals negative 8a plus 4c. And that's all I can do with my function. Okay? So this is going to turn into a systems problem. Okay, so now let's find our derivative. We got some points to put into there. So that's all I could do with f of x. I plugged in 0, 6. I plugged in negative 2, 8. I'm done with my first function. Now let's take the derivative of this. So this is 3ax squared plus 2cx, and d is a constant, so plus 0. And we're going to do the same thing. Okay? Now, before I plug in 0, 0, so I've got 0, 0 to plug in and negative 2, 0. But if I put in 0, 0, that's not going to really help me much, right? Because I'm going to get 0 equals 0 plus 0. That doesn't help me. So using 0, 0, I'm going to just say using 0, 0 is no help. So I'm going to move on, okay? Because plugging in all zeros is useless to me. So all I really can do is plug in negative 2, 0 into the derivative, and let's see what happens. So I'm going to use negative 2, 0. So y is 0, x is negative 2. And then we can simplify that. So this is 4 times 3, so that's 12a minus 4c. Right? And now I got a nice little systems, and it's easy because I got the 4 c's right there. So now I have this and this, get 2 functions with a and c. And because I see that I have a positive 4c and a negative 4c, I'm going to use elimination. Remember how to solve systems. You can do substitution. All right, so I'm going to take these 2 guys, and I'm going to solve. So if I'm using elimination, I'm going to line them up. It's a lot of work. That's why I don't give this one on the test. It's not a hard problem. It's just a lot of algebra. All right, so we're going to add our columns. Since I already have eliminating going on. So 2 equals 4a. C's are going to cancel out. So a is 2. And lastly, I got to find c. So you can plug in your a value to either one of these. I'll just use this one. It seems easier. So let's plug 2 into there. Okay? So that's 0 equals 12 times 2 minus 4c. So 12 times 2 is 24. Move the 4c over. So c is 6. I did something wrong there. Yeah, I don't know what I'm doing.
We learned it anyways. What is all this numbers?
What am I
Isn't it 0.5?
Yes.
Yeah,
Right?
it's Monday.
Agreed.
All right.
There we go.
A is 1/2. Yeah, I just saw that. All right, sorry about that. That's you guys know that mistake, right? That's the easy mistake. All right, so plug in 1/2 now. Whew. All right, so A is 1/2. I thought C was going to be a fraction. All right, so 12 times 1/2 is 6. Now move the 4c over. So we get 6 over 4, 3/2. All right, so there are your A, C, and D values, so you can write your function. I think WebWorks just wants those values. I'm glad you guys found that. All right, good? All right, so that one is WebWorks. It's not fun, but yes.
So what we'll put in WebWork is just the A and the C. We're not going to put the whole function value in there.
I think it just asks for the letters, but like, so if you were going to write the function, then you would just say 3/2 x cubed plus, no, sorry, 1/2 x cubed plus 3/2 x squared plus 6. But I think it'll just give you lines for A, C, and D, if I remember right. Okay?
I was going to ask,
Uh-huh.
how did you know to set the functions up to one another and add them together?
Because when you're solving so I only had those 2 ordered pairs for f of x, right? So I did what I could, but it still ended up with 2 variables. So typically in math, when you have a function with 2 variables, and then that has to be a system. That's the only way you can solve it, is you got to have another equation with those same 2 variables. So that's the way that this problem is set up. So that once you're simplifying them, you end up with 2 variables and 2 equations. And that has to be done as a system. Okay? So that's just one of the rules in math. You can't solve an equation with 2 variables with 1 equation. So you need those 2. All right. Okay, so we can stop recording section 4.3. Okay. Anything else on that one?